Today's final speaker, Dr. Danny Coffey, is an assistant research scientist at the Heart Research Institute for Gulf of Mexico Studies at Texas A&M University, Corpus Christi. He has over 10 years of experience using animal-borne tracking technologies as research tools to monitor the movement and behavior of sharks and fishes across different spatial and temporal scales. This information is used to investigate the underlying ecological and physiological drivers of habitat use that are informative for managing and conserving living marine resources. So I will now hand it over to Danny for our final talk of the day.
Thank you very much for the introduction, Lauren. Hi, I'm Danny Coffey, and it's my pleasure to be presenting at this year's Sitka Whale Fest. So sharks and other marine animals live in a concealing environment, and I will be talking about some of the tools that we can use to reveal the secret lives of cold water sharks while they remain hidden underwater and out of sight. To start, I'd like to introduce you to my story. That's me as a little boy, and yes, that's a blonde mullet. I wasn't in charge of my haircut until I was several years older, and you can thank my parents for that who should be listening to this talk. I was originally fascinated with dinosaurs and loved digging trying to find them, but not too much later, my interest shifted to another group of animals that were alive during the age of dinosaurs, but still exist today, sharks. However, I did not know how to have a career working with sharks outside of an aquarium since I had never before met a marine biologist. Years later, I ended up going to college at University of California, Santa Cruz, and majored in legal studies since I was actually planning at that point in time to become a criminal investigator. It was at UC Santa Cruz that I learned about a career in marine biology, and I switched my major halfway through. Looking back, I now realize both scientists and detectives are actually quite similar in that they make an observation, form a hypothesis, gather data or evidence, and then present that information to their peers for a consensus. One of the turning points was reading a book by Susan Casey called The Devil's Teeth, where she followed a group of scientists on the Farallon Islands off the coast of San Francisco, where they noticed white sharks appeared every fall and winter and then suddenly disappeared. So they started putting tags on them to figure out where they go. And I became very interested in this emerging field of research known as animal biotelemetry. It wasn't actually until the age of 24 that I finally got to realize my childhood dream of working with sharks. And lucky for me, it was tagging white sharks with the same scientists in the Devil's Teeth. My master's advisor told me that I was the most persistent person she had ever met when I was trying to get into her lab. And that just goes to say that persistence will pay off in the end, even if it takes a little longer than you originally hoped for. Today, I'll be talking about two sharks found in Alaskan waters, specifically the salmon shark, who manages to live life in the fast lane, powered by mammal-like muscles, and the blunt-nosed six-gill shark, a living fossil who takes on a much slower approach to life in the cold. Most people outside of Alaska wouldn't expect to find a voracious shark predator in these cold waters, but therein lies the salmon shark. Aptly named after one of its primary prey species, salmon sharks are also known to prey on herring and sablefish that Steve, Eleni, and Matt talked about earlier. To learn more about where salmon sharks go, we traveled to Prince William Sound to attach satellite tags to their dorsal fins, which transmit their location whenever they're at the surface. And if you look closely, you can actually see the satellite tag on that salmon shark as it chases its prey. We tagged almost 100 salmon sharks that revealed highly migratory movements throughout the eastern North Pacific. Sharks were present off Alaska year-round with a peak occurrence during summer and autumn, while some sharks began migrating to lower latitudes during autumn and winter. If we color code these tracks by the temperature of the ocean surface, it revealed salmon sharks encounter a wide range of temperatures, from the cold subarctic waters off Alaska in blue to warmer subtropical waters nearing Hawaii in red. So how are salmon sharks able to exist in such cold, high-latitude waters? It turns out they have a very unique physiology. All sharks in the family Lamidae, including salmon sharks, port eagle sharks, two species of mangrove sharks, and white sharks, have some degree of endothermy, which Matt introduced earlier. And this means that their internal body temperature is warmer than the surrounding environment. But the expression of these traits is considered greatest in the genus Lamna, which includes salmon and port eagle sharks. In Lamna sharks, red muscle used for sustained swimming is concentrated near the center of the body and generates heat. The body then retains this heat using a countercurrent exchange mechanism in their blood vessels. This allows salmon sharks to have internal body temperatures over 30 degrees warmer than the surrounding water. For typical ectothermic fish on the bottom, such as a salmon, their body temperature is typically the same as the surrounding water. This graph shows that endothermic sharks and fishes, such as lamprey sharks and tunas represented by red shapes, are able to swim faster and migrate further than other ectothermic fish, such as blacktip sharks and Pacific halibut, which are represented by blue shapes in the lower left-hand corner. And this gives endothermic fishes, such as salmon sharks, a significant predatory advantage.
Danny, can you hear me? This is Lauren.
Sorry about that.
The audio is breaking up quite a bit. So they're suggesting maybe we should have you turn your video off.
Sorry.
Can you hear me? We're your audio is coming in and out. So we're suggesting maybe you turn your video off and just use the audio.
Okay.
And we'll see if that makes the audio come in better. Okay, let's see if we can hear you now better.
Okay, does that sound better?
Yeah, that sounds great. Wonderful. Okay, we'll just continue from there. Sorry about that.
Okay. So salmon sharks also have a very unique cardiac physiology, and it's highly specialized for utilizing cold habitats through the increased expression of the proteins that are required for contracting and relaxing the heart. Salmon shark hearts, shown in red, are able to maintain function at low temperatures all the way down to 5 degrees Celsius, thereby providing their active warm tissues with enough oxygen to effectively forage in cold environments. You'll notice the heart functions more similarly to a warm-blooded rat, shown in black, than an ectothermic blue shark, shown in blue. This unique physiology allows salmon sharks, shown in blue, to occupy colder waters of the eastern North Pacific compared to their endothermic cousins in the same family, such as white sharks in black and mako sharks in red, which are restricted to slightly warmer waters in lower latitudes. In addition to tagging salmon sharks with dorsal fin mounted satellite tags or spot tags, we also double tag them with a pop-up satellite archival tag or PAT tag. PAT tags record depth, temperature, and light data and are programmed to detach from the tagged animal and float to the surface. Once at the surface, PAT tags transmit summaries of the environmental data to orbiting satellites. Compared to dorsal fin mounted spot tags, these tags allow us to visualize the movements of salmon sharks across their full three-dimensional environment. And they also don't require the shark to come to the surface. I'll walk you through 3 salmon sharks that were double tagged in the same place in Prince William Sound, yet had very different migratory patterns. You'll notice not all 3 migrated south, and this is what is known as partial migration. The first shark overwintered in cold Alaskan waters outside of Prince William Sound. The bottom figure shows the daily maximum temperature, the daily maximum depth for this shark and is color-coded by water temperature. And the black line represents its average depth during the night, and the white line represents the average depth during the day. You'll notice that typically the shark is deeper during the day than at night. However, this switches during the winter and spring when the shark stays below 50 to 100 meters, or about 150 to 300 feet throughout this entire period. And this is because of a very unique phenomenon in Alaskan waters known as an inversion layer, where the surface waters are actually colder than deeper waters. And this salmon shark is in fact remaining deeper to stay warmer. The second shark spent a few months in Alaska before migrating south to an area known as the subtropical gyre, southwest of California, where it began diving to deeper waters around 400 meters or 1,200 feet before circling back towards Alaska. The last shark left Alaska almost immediately and swam to the subtropical gyre before migrating east to overwinter in the California current. You'll notice that the waters of the subtropical gyre are much warmer during November and December compared to when a previous shark visited in March. If we look closer, the average daytime depth, which remember is in white, and the average nighttime depth in black, reveal this salmon shark would remain below that warm blob of red where temperatures exceeded 20 degrees Celsius or 68 degrees Fahrenheit. This same behavior is noticeable in the dorsal fin-mounted satellite tracks, where salmon sharks are not coming to the surface in the warmer waters close to Hawaii, even though some pop-up tags were released in Hawaii as shown by the red triangle. Therefore, when some waters were just too cold off Alaska or just too warm off Hawaii, salmon sharks would dive deeper to find refuge at temperatures that were just right, kind of like the story of Goldilocks and the Three Bears. Pop-up satellite tags have also been used to investigate the movements of salmon shark prey, including large Chinook salmon, and sometimes can reveal direct evidence of predation. For example, in this figure, the black dots represent depth and the blue dots represent water temperature recorded by the tagged salmon. And suddenly on October 21st, the temperature shifts from around 7 degrees to 27 degrees, and the depth behavior changed with more surface-oriented behavior. Using these clues, scientists concluded that this salmon was actually eaten by a salmon shark based on the elevated temperature recorded inside the shark's stomach, which is similar to the internal body temperature of a salmon shark. Similarly, this Chinook salmon was also eaten by a mysterious predator on November 30th. Can you guess what it is? Based on the dive profiles, including a lot of surface-oriented behavior and temperatures rising from around 7 degrees to over 35 degrees, scientists predict this salmon was in fact eaten by a resident killer whale. You'll notice killer whales maintain a body temperature that is still much warmer compared to salmon sharks, which are around 27 degrees. And lastly, the predator who ate this Chinook salmon did not increase stomach temperatures above surrounding water temperatures when this individual was eaten on November 17th. So what that tells us is that this was an ectothermic predator. Based on the very deep swimming behavior around 75 meters, it was predicted that this salmon was either eaten by a Pacific halibut or a sleeper shark. Salmon sharks are not really a danger to people. However, they have encountered conflicts by stealing bait or catch off fishermen's hooks, such as this half-eaten halibut on the left. And this is known as depredation. And at times, this results in a shark being captured or killed, whether it's unattended or on purpose for sport fishing. Those salmon recreational fisheries in Alaska have been managed for quite some time and restrict anglers to only 2 sharks per year. Salmon sharks are also captured incidentally in commercial fisheries like this trawl net. And this just goes to remind us that when it comes to the ocean, we as humans are the ultimate apex predator. This graph shows the probability of encountering a salmon shark in different management zones throughout the year. And satellite tracks reveal the highly migratory movements of salmon sharks requires cooperative management across 3 countries, including the United States, Mexico, and Canada. However, salmon sharks also spend a high proportion of time in international waters of the high seas, particularly during the winter and spring, which is not very well regulated, and this is an ongoing issue worldwide. Next up, I'm going to talk about another Alaskan predator, the blunt-nosed six-gill shark. Six-gill sharks belong to the oldest group of sharks, hexanchoforms, made up of only 6 species that still exist today. And they're characterized by 6 or 7 pairs of gill slits in a single dorsal fin, whereas other sharks have 5 pairs of gill slits and 2 dorsal fins. Six-gill sharks evolved 196 million years ago during the Triassic period and are considered a living fossil today. So in a way, I'm still able to study a living dinosaur. This six-gill is swimming at a depth of 75 meters near the Channel Islands off Southern California. However, when searching for six-gills in the warmer subtropical waters of the Pacific, we must go below 200 meters or 600 feet into the deep sea, which you learned about yesterday during Jim Barry's talk. While remotely operated vehicles, such as shown here, provide fascinating images of these sharks, including a male and female shark swimming side by side, we need to use a different set of tools to learn more about these highly mobile predators. Off Hawaii, we combined a novel suite of tagging technologies to examine the depth, internal body temperature, environmental water temperature, and dissolved oxygen of free-swimming six-gills. We also attached an accelerometer, which measures activity levels of the shark similar to a smartwatch or a Fitbit that you might wear. After 4 to 6 days, the package releases from the shark and floats to the surface, where it has satellite transmitters on board that allow us to locate and retrieve the device in order to download this very high-resolution data set. These tags revealed six-gills undertake vertical migrations to deeper depths during the daytime, represented by white bars, that are closely tied with the timing of sunrise and sunset, with periods of nighttime shaded in gray. This behavior is similar to the vertical migrations of salmon sharks I showed earlier in the subtropical gyre, and are likely reflect the pursuit of prey. However, six-gills dive much deeper and never come shallower than 200 meters or 600 feet. Temperature data measured by the tag suggests temperature may be an important driver of vertical behavior, as six-gills occupy stable cold temperatures around 5 degrees Celsius or 40 degrees Fahrenheit at greater depths during the day, and encounter a range of temperatures at night. Using novel tags equipped with oxygen sensors, we were able to measure the dissolved oxygen levels experienced at depth by these six-gill sharks, which are as low as 9% saturation. And this demonstrates a tolerance to hypoxic or low oxygen conditions. And what that means is that the oxygen levels are less than 10% of what you would find near the surface. Using the accelerometer data, we predicted that six-gills would have lower activity levels represented by orange circles during their deeper daytime distribution in cold, low oxygen waters. However, as you see here, much to our surprise, six-gills actually had higher activity levels represented by blue circles under these very harsh conditions. Analyses of body temperature represented by the red line revealed six-gill sharks spent most of their deeper daytime distribution, represented again by white bars, with core body temperatures that were in fact warmer than surrounding water temperatures, represented by the black line. The large body mass of six-gill sharks slows heat loss during their descent into cold, deep waters and may enable them to maintain relatively high activity levels. So while six-gills do not have an endothermic capacity like salmon sharks, they are still able to take advantage of warmer body temperatures just by being so massive. For example, we measured six-gills to be over 6 feet around at the center of their body. Think of putting a large steak in the freezer. The outside will cool much quicker before the inside reaches that same temperature, and six-gills are able to exploit this difference. Using longer-term deployments with pop-up satellite tags, we revealed 6 gills undertake these same vertical migrations every single day, as shown here by this 200-day track. So this begs the question, what limits the vertical habitat of 6-gill sharks? 6-gill sharks live in shallower waters at higher latitudes, such as this diver swimming with one in Puget Sound, Washington. But they experience a similar range of temperatures to those found in the deeper waters off Hawaii. In other locations, the warmest temperature at which a 6-gill shark was observed was 17 degrees Celsius, or around 62 degrees Fahrenheit. In Hawaii, they spend very little time in waters exceeding 17 degrees Celsius, which suggests that these warm temperatures may in fact be physiologically limited. And if we plot the depth of where you would find 17 degrees Celsius in Hawaii across our original long-term track, it corresponds very well to the upper limit of this 6 gills vertical distribution. But what sets the lower limit of its vertical distribution? 6-gill sharks are often thought to be associated with the seafloor, including shallow cold water habitats in the US Pacific Northwest on the left and deep water habitats in the Gulf of Mexico on the right at a depth of over 1,800 feet. To investigate the habitat of 6 gills in Hawaii, we attached an animal-borne camera, which you can see on its right pectoral fin. These cameras would take a series of still images and then eventually detach from the shark and float to the surface, similar to the other packages, where we could download the video data. This camera recorded still images of the seafloor at a depth of 2,600 feet, but only during the daytime, as well as images of other species or potential prey. However, one study tagged a 6-gill shark off Hawaii, which swam almost 1,000 kilometers over open ocean a few thousand meters deep. And yet the transmitted depth data revealed this shark still rarely swam below 700 meters, even though the seafloor was a few thousand meters deep. Therefore, it may not be the ocean seafloor that is in fact limiting the depth of these sharks. A depth profile of temperature in red and dissolved oxygen in blue reveals the depth of the local oxygen minimum zone, or where oxygen is the lowest in Hawaiian waters, occurs at around 750 meters at a concentration of 30 micromoles per kilogram. In comparison, there is a relatively gradual decline in temperature, as shown by the red line, at the same depth. The deeper daytime distribution of 6 gills is generally between 500 to 700 meters, just above this local oxygen minimum zone. And in fact, the minimum oxygen level experienced by a species may often be very close to its physiological threshold. As a result, the local oxygen minimum zone may be what's directly limiting the lower limit of 6 gills, or alternatively, it could be indirectly limiting their preferred prey. If we add the depth of the 30 micromole per kilogram isopleth across our original long-term track, the lower limit of this 6 gills vertical distribution generally resides above the oxygen minimum zone. The 17 degrees Celsius isotherm and 30 micromole per kilogram isopleth also both constrain the vertical distribution of this similarly sized 6 gill across its 200-day track. 6 gills have a global distribution along most coastlines and around the world, highlighted here in yellow. Therefore, we can maybe use them as a critical marker for indicating how climate change will impact deep sea ecosystems. If we compare the current depth of the 17 degrees Celsius isotherm on the left with future conditions on the right, we see globally that the depth of the 17 degrees Celsius isotherm will deepen across the entire range of 6 gill distribution, as shown in red, under future climate change conditions towards the end of the century. At the same time, the depth of the 30 micromole per kilogram isopleth, the dissolved oxygen level that is critical for limiting their lower depth distribution, will rise in some habitats, as shown in blue on the figure on the right. And this will also occur in new areas where it does not currently exist. So what this means is, taken together, the combined effects of global warming and oxygen loss will expand the vertical habitat of six-gill sharks in some areas, as shown in blue on the figure on the right, and compress in others, as shown in red. And this is particularly true within the Hawaiian archipelago, highlighted in the red box. This goes to show that we as humans are impacting top predators such as sharks directly by fishing for them, as shown by the example with salmon sharks, and indirectly through climate change, as shown by these deep water six-gills. Collectively, our role as the apex predator in marine and terrestrial ecosystems has become unbalanced, but there is still time to change it. And with that, I would like to acknowledge all of the funding sources who contributed to these studies, as well as Wildlife Computers, who is the manufacturer who makes these amazing devices that without which we wouldn't be able to understand where these animals go. And with that, I would be happy to take any questions. Thank you.
All right, thank you so much for that talk, Danny. That was really interesting stuff. Okay, we are going to do some questions here. Let's see. What do we have? So you, as a reminder, you can put your questions in the Q&A on whova.com. All right, so here's the first question. How do you find sharks to tag? Uh-oh, can you hear me, Danny? Oh, he can't start his video or hear anything. Uh-oh, okay. Technical difficulties, everyone. Hold on just one moment and we'll try to see if we can get Danny back on. Oh, now we see you.
Can you hear me?
Yep, we can hear you.
I can't hear you, unfortunately.
Here, maybe we can, I'll type the question to you in the chat. So the question,
I'll come, maybe leave and come right back.
okay. Let's see. Yeah, we'll get Danny right back in there. He was unable to hear us. So sit tight for a second, everyone. And we'll have Danny back in just a minute to answer some of our questions. In the meantime, I'll take this opportunity to remind everyone that it's daylight savings time tonight. I'm sure you're thinking I'm a broken record at this point. But don't forget to set your clocks back, spring forward, fall back. And looks like we have Danny back on. Can you hear us now, Danny? Oh, we can hear you.
What's happening?
Let's see. We can hear you, but you can't hear us, it sounds like. Maybe our tech person can help out with that, because it looks, I'm trying to message you in the chat, but it's not working for me to message you either.
Okay, I'm good now.
Oh,
okay.
You can hear us.
Yes,
wonderful.
Finally. Sorry about that.
I was out of solutions.
Yeah,
okay, so the first question for you was, how do you find sharks to tag?
How do we find sharks to tag? So I'll start with the salmon sharks. That came from just using local fisherman knowledge, where we knew that they aggregated in Prince William Sound during the summer season. And so as you saw, only some of them would stay there for that period of time and then they would take off. So we would target our efforts usually from June and July, as late as August. So sometimes you need a little bit of background information from the local community, which is also very helpful. For six-gills in Hawaii, most people who are not scientists have no idea that they even exist there, because they would never be fishing below 600 feet. So we we're fortunate enough that the Hawaiian Islands, as most people realize, are volcanic islands that rise up very quickly from the seafloor. And that means you don't have to go very far to find deep water. So we would actually take a 10-minute boat ride from our marine station and set our gear at the mouth of a submarine canyon. And that would allow us to get to 300 meters depth within a 10-minute boat ride, which now I'm in the Gulf of Mexico, and that would take probably at least 3 hours on a very fast boat. And we knew that six gills are these diel vertically migrating sharks. So they spend most of their nighttime at shallower depths, shallow still being pretty deep, around 300 meters. And we would set our gear at that nighttime depth and then come first thing in the morning, haul it up, tag the shark, and then quickly release them back to their depths.
Oh, very cool. Very cool. Okay, let's see. Another question that got a lot of votes was, do you believe that sharks can reach great sizes and survive in high pressure environments deep in the ocean, such as the megalodon?
Sharks can survive in very deep environments. However, they have not been found on the abyssal plain, which is usually around 4,000 meters, which is actually the average depth for a lot of the ocean. They're usually limited to around 2,000 or 2,500 meters. And it's still, there's a couple theories as to why they're not able to surpass that depth. That might have to do with their physiology. But as in terms of a megalodon, they do not still exist today, even though there have been some Discovery Channel mockumentaries about them. But at this point, even though there's still a lot of the deep sea for us to explore, I don't think we would miss something that large. And plus, something that large would also need an insane amount of prey to feed on, and it would have to come up to closer to the surface probably to find that much of prey resources.
That makes sense. Okay, so we have a question about, do you ever tag baby or younger sharks? Is there a specific age range that you seek for the ideal shark to tag? This person was curious because if their age plays a role in the behavior over time.
Yes, that's a really good question, actually. And so for a lot of different tagging technologies, the tags can be quite big. And so we're limited on the size of the animal. And so for a lot of species, we're not able to study some of the earlier age classes for that reason, because we have an ethical responsibility as a scientist to not put a tag on a shark that's too small for it, that we would, and also our goal is to observe its natural behavior. So we don't want to impact its natural behavior in any way. However, for a lot of smaller size sharks or even fishes, we use acoustic technology, which Matt talked about briefly earlier with sablefish. And so those tags can be very tiny, an inch or even smaller. And so those allow us to study smaller sharks that usually might not move as much as an adult. So you'll definitely see changes throughout their life history.
Nice. Okay, so then we have someone asking, what's the rate of loss of these trackers of the 6-gill sharks when they're released? So I guess the tag loss rate.
The tags that we were using are meant to remove or meant to release from the animal. So we want them to lose it, but we want the animal to carry it for the desired period of time. So we actually had 100% success rate with recovering all of those packages at sea. And that was also why we did short deployments, which were only about 6 days. So that way we would have a good weather window in the future to be able to go and recover the tags. However, those 200-day tracks I showed you, those tags are designed to just pop off and transmit their data, and you don't need to physically recover them. But we actually physically recovered those tags, which gave us access to that great data. And it was amazing that over 200 days, those two 6-gills actually didn't swim more than, one swam a couple miles away, and the other one swam about 60 miles away, which is not very far for a 200-day trek. So we think that they might want to stay resident to the Hawaiian coastline.
Oh, wow, that's really interesting. Okay, let's see. Have you seen interactions? So this is back to the part about the salmon sharks. Have you seen interactions between resident killer whales and salmon sharks?
I have not seen that. I knew of interactions between killer whales and white sharks out at the Farallon Islands, which was where that book, The Devil's Teeth, was based off of. And what's interesting is researchers that are working there have noticed through their tracking data that sometimes those white sharks will actually completely leave the Farallones and not come back when a pod of orcas are coming into that area. So it just goes to remind you that even though great whites are a apex predator in their own right, that the killer whale still reigns supreme. But unfortunately, I don't have any information regarding killer whale and salmon shark interactions.
That's good. Yeah, the killer whales are pretty voracious. Okay, let's see. Oh, here's a good question for you. How much does it cost to conduct all of this research?
That's a really good question. These tags, unfortunately, are not cheap. The real reason we even have access to this technology is because it's borrowed from human technology. As I mentioned, those accelerometers that measure the activity of six-gill sharks are the same technology that's found in your smartphone or smartwatch or your Fitbit. And it's that wide production for humans that made that type of technology affordable enough that the relatively few companies, of which there are probably only 3 or 4 that make animal tracking tags, can borrow it, and then they still have to sell it for a premium because they're relatively small companies. So the tags on the salmon sharks, the dorsal fin mounted one, the spot tag that just kind of gives you horizontal tracks, is about $2,000. The pop-up tag is $4,000. And then what we put on the 6-gill was a whole suite of tags that came up closer to about $10,000. And that's just for the tag itself. Then you have to factor in boat time and fuel and bait and fishing gear and all of these other things. So it can add up quite quickly. That's why it's fortunate if you're in Alaska or Hawaii or somewhere where you have access to these animals just a stone's throw away.
Yeah. Yeah, our sperm whale tags are a couple $1,000s each as well. So it gets expensive. And I think people are really interested in how much it costs to do research. And like you said, on top of just buying the equipment, you then have to pay for the vessel time and the crew time and your salary while you're out there. So it can definitely add up. Let's see. Here's a popular question from Simon. What are your thoughts on why some salmon sharks migrate? Would it be food abundance, specific to temperature changes? Any thoughts there on why they migrate?
It's also a really good question. Something that I didn't mention was that all the salmon sharks tracked in that study were females.
Oh.
And that's not for a lack of trying to find a male. It's just that salmon sharks live across the entire North Pacific. However, they tend to sexually segregate, and you're more likely to find a male salmon shark on the Western Pacific off of Russia and Japan and Asia, and you're more likely to find a female in the Eastern North Pacific off of the US and Canada. However, obviously they must mix somewhere. And there was a recent study actually a year or 2 ago that tracked the first 2 male salmon sharks in the Bering Sea. So with that in mind, salmon sharks, we believe that they're going to the subtropical gyre, to those warmer waters to pup. And a lot of shark species, including salmon sharks, won't pup every year. So some of them may stay in Alaskan waters because they're, as I showed, they're able to withstand those cold waters. There's food there year round, and it's very energetically expensive to make these large scale migrations. So if they're not pupping, then there's really no reason to leave. However, if they are pupping, then they're going to go to a area such as the subtropical gyre that's warmer and a little bit more hospitable for their pups to survive before they might eventually migrate back to the coast.
Nice. Yeah, got to look out for the little ones. Let's see. Okay. Is the size of the shark heavily determined by specific areas or environments? So this person, I guess, is kind of interested in how sharks get to the size that they are.
Yeah, so just as I said that some shark species will sexually segregate, whether you're a male or female, they'll also segregate based on size class sometimes. And that's because for some sharks, like salmon sharks that have an endothermic capacity, they probably don't have such a great endothermic capacity when they're younger. So that's why they want to be in warmer waters in the subtropical gyre or even off the California current. And it's not until they're becoming subadults or adults that they have this full suite of endothermic capacity that they could actually withstand the cold waters of Alaska. Also, small sharks and big sharks don't mesh well together, and that small sharks of the same species can also be prey to larger sharks of the same species. So that's also why sometimes nursery habitats will be in areas that are different from where the adults like to spend most of their time, because you could lose a lot of those offspring to hungry adults. So for the six gills, it was really interesting that we've never seen a small six gill off Hawaii. We know they exist, like in Puget Sound, they usually see much smaller six gills. Don't get me wrong, they're still very large. But compared to the sharks we see in Hawaii, we're seeing they're almost always between 3 or 4.5 meters. So that's around 10 to 15 feet. Whereas the ones you'd find in Puget Sound are slightly smaller, and that might be because that's an important nursery habitat.
Okay. All right, let's see. Here's a question. Do sharks actually sleep?
That's a really good question. I think it's some sharks have to, like the salmon shark, are known as obligate ram ventilators, which means they have to continually swim in order to get oxygen and water over their gills so that they can breathe. There are other sharks, such as nurse sharks, that can actually actively pump water over their gills, and they don't need to constantly swim. So at least for the obligate ram ventilators, such as salmon sharks, I think it might be something similar. I'm not quite 100% sure, but I think it's probably a similar mechanism as for like marine mammals such as dolphins, where they can kind of put themselves partially to sleep, but they're still continually moving and swimming. So they're resting, sort of peak. They're not actively hunting, but they still need to keep moving. So they're not totally taking it easy.
Okay. All right, I think we have time for just a couple more. I'm going to combine two questions. So it'll be a two-part question. What is your favorite Alaskan shark? And then what is the most difficult part and rewarding part of tagging sharks for you?
So my favorite Alaskan shark would have to be the salmon shark. They're just so interesting in terms of their physiology and how they go. You'd never think that a salmon shark would swim from Alaska to Hawaii. And they don't get a lot of credit where credit is due, because most people, they're usually outshined by their more popular cousins, like the white shark and mako shark. So I think salmon sharks deserve more credit. And in terms of what's the most rewarding part of my job and
the most difficult.
And the most difficult. The most rewarding is getting the chance to be up and close with these amazing animals. Like I said, almost no one in Hawaii, unless you went down in a submersible, would ever see a six-gill shark. And so getting to see these amazing animals is a really great experience for me, especially that we're tagging them and releasing them, so their survival is our highest priority. And the most difficult thing would be, there's a lot of effort you have to put in, and you kind of got a highlight reel from this presentation, but there's a lot more opportunities out there where you never see a shark and you put a lot of energy and time and effort and money. And I wouldn't really consider that too much of a challenge, but it can be over time to actually interact with these animals and make sure that they're healthy when you catch them. And the cost, I guess, is the most difficult thing is writing grant money to do these things.
Yeah, and that's a good thing to bring up for our students, that all of these things do cost money, and we have to find that funding for our research. So, okay, looks like we are out of time for questions. Another virtual round of applause for Danny. Thank you so much.